Hello and welcome back. In this tutorial, we will study logarithm. First, let us think about what is a logarithm. Logarithm is an inverse function of the exponential function. So if we draw an exponential function, y equal a to the power of x, any inverse function would be symmetric about the following line. Bisectries. First, let us think how we can construct this symmetry. Well, we know that any exponential function passing through this point, 0, 1. It means that function symmetric about this line will also pass through some point. Let us think which point it would be. So in other words, how to construct point symmetric about this line, point symmetric to point 0, 1. So if we take some perpendicular and we push it further with the same distance, we obtain the following point. And this point will be point 1, 0. Now we can think about how to construct symmetry. So if we take this function and flip symmetrically about these bisectries, we obtain the following function. And this function is called logarithmic function. And we denote it as y equal logarithm of x with base a. So what are the properties of the logarithm? If you look at this function, you can see that the domain of the function would be from 0 to positive infinity. Logarithmic function will never intersect y-axis. So domain is interval from 0 to positive infinity. And range, if you look over y-axis, so the range of the function is from negative infinity to positive infinity. As you see, this domain and range is just opposite to domain and range of exponential function. With exponential function, domain was whole real line, and the range is from 0 to positive infinity, and now it's vice versa. Let us think about logarithm as a number first. Logarithm of b with base a. So again, logarithm is at which power I have to raise number a in order to get b. For example, if we wanted to find logarithm of 32 with base 2, it means that I have to find at which power I have to raise 2 in order to get 32. And we can find that 2 have to be raised to the power 5 in order to get 32. So logarithm of 32 with base 2 is just equal to 5. Or another example. What is a logarithm of 0.04 with base 5? So again, I have to find at which power I have to raise 5 in order to get 0.04. Well, apparently we can play a little bit here, and I can think about the following. 0.04 is the same as 1 divided by 25, and 1 over 25 is the same as 1 over 5 to the power of 2. So in other words, we have the following relation. And this is the same as 5 to the power of negative 2. So we have that we have to raise 5 to the power of negative 2 in order to obtain 0.04. So logarithm of 0.04 with base 5 is equal to negative 2. So in general, if we think about logarithmic function, we have y equal logarithm of x with base a. And this is inverse function to exponential function. In other words, if we wanted to find x, x will be equal a to the power of y. we have some notations for the logarithm. The general logarithm denoted as logarithm of x with base a. Now, if we wanted to use logarithm with base 10, we would just use the following notation, log of x. So if you don't see any base for the logarithm, it means that base of this logarithm is just 10. And logarithm of x with base e, where e, you remember, our special number, 2.71, is denoted as ln x. This is called natural logarithm. And the reason why we have this short notation, because this natural logarithm used a lot in the applications. So we just wanted some short notation for it. Let us study some properties of the logarithm. Logarithm of x times y with base a. This is the same as sum of the logarithms. Logarithm of x with base a plus logarithm of y with base a. Also, we can proceed with the quotient. If we have logarithm of x divided by y with base a, this would be the same as difference of the logarithm. So it's logarithm of x with base a minus logarithm of y with base a. Another very important rule is the following. If we have logarithm of x to the power of b with base a, and be careful here that actually x is to the power of b, not the whole logarithm, but whatever is under logarithm is raised to the power of b. Then we can just take this power and pull it in front of the logarithm. So it would be equal to b times logarithm of x with base a. Another property is that logarithm of 1 with any base is always equal to 0. It's because any logarithmic function passes through the point 1, 0. Also, if we have logarithm of a with the same base of a, it's just equal to 1. And now two more important properties. If we have logarithm of exponential function a to the power of x, and we take base of the logarithm also equal to a, same as the base of the exponential function, this is just equal to x. Now vice versa. If we take exponential function, and the power of this function we take as a logarithm with the same base as exponential function, logarithm of x with base a, this will be just an x. In order to solve some equations, we always should think about the following rule. If logarithm of x with base a is equal to logarithm of y with base a, it will happen if and only if x is equal to y. Same as with exponential functions, right? So we have logarithm with base a in both sides of this equation, so whatever is under logarithm has to be equal. Let us do some examples now. Let us simplify the following relation. Logarithm of 72 minus logarithm of 9 divided by logarithm of 28 minus logarithm of 7. As you see, I don't have any base under my logarithm. It means that my base is equal to 10. Let us simplify this relation just using properties of the logarithm. First, let me consider numerator. Logarithm of 72 minus logarithm of 9. Here I have difference of the logarithm, and I can write it using law of logarithm as the division. So it will be the same as logarithm of 72 over 9, which I can simplify actually further to obtain that it's logarithm of 8. can play with this even more. I can represent 8 as the power of 2. So it's logarithm of 2 cubed. And now, using property of logarithm, I can take this power and bring it outside of the logarithm. So it would be the same as 3 logarithm of 2. Now let us do the same with denominator. We have logarithm of 28 minus logarithm of 7. Again, by the property of logarithm, I will represent this as the quotient. So it's logarithm of 28 divided by 7. Now we can simplify. It's the same as logarithm of 4. And now 4 I also can represent as power of 2. So it's logarithm of 2 squared. And as before, power can be bring outside of the logarithm. So it's the same as logarithm of 2 with 2 in front. In numerator, we obtained 3 logarithm of 2. And in denominator, we obtained 2 logarithm of 2. Look, logarithms now cancel. And what we have? Just 3 over 2. You see, such a simple number 3 over 2 can be represented in terms of logarithm, in terms of very complicated stuff. Let us try to solve some equations now. Before, we would solve equation with exponential function as the following. 2 to the power of x equal to 4. What we've done before, we would represent 4 in terms of 2 squared, and we would say that since the bases are equal, then the powers are equal. From here, x is equal to 2. Now the question is, what happened if we cannot represent right-hand side in terms of the base of the left-hand side? In other words, how we would solve, for example, equation 2 to the power of x equal to 3? Well, we have 2 logics for that. Logic 1, 2 to the power of x is equal to 3. So basically what I wanted to do here, I wanted to pull this x downside, right? I wanted to drop this x down, and in order to do that, I have to take 2 out. It's like I'm sitting in the chair, and if somebody takes this chair out of me, I'm going to drop down, right? So we wanted to take these 2 off. How we can do that? Well, we know the following property of logarithm. Logarithm of a to the power of x with the same base a is just equal to x. So in other words, these guys eat each other. So in order to make these 2 disappear, I have to act by logarithmic function with the same base 2 on both sides of this equation. Right? Do you agree that if a is equal to b, and if I use the same function on both sides of this equation, the relationship still remains to be the same? And this is what I'm going to do now. I'm going to take logarithm with base 2 because I have exponential function with base 2, on both sides of this equation. So I have 2 to the power of x equal to 3, and I'm taking logarithm with base 2 on both sides of this equation. Now, using property of logarithm, what happened? These guys disappeared. So my x dropped down, and I obtained x is equal to logarithm of 3 with base 2. And this would be an answer, because logarithm of 3 with base 2 is just a number, which we can calculate approximately. Logic 2. Again, we wanted to solve equation 2 to the power of x is equal to 3. Well, we can think about the following situation. When x squared is equal to y, how we would solve this equation for x? We would take square roots of both sides of this equation, right? So x will be equal positive or negative square root of y. How do we know that I have to square root this? Well, x squared and square root, they cancel each other because they're inverse functions to each other. Same with exponential function and logarithms. Remember in the beginning, I would say that logarithm of x with base a is equal to y. Then how to find x? From here, x will be equal a to the power of y. So in other words, if we have this relationship x equal to a to the power of y, in order to find y, I basically take this a and move it into the other side, and it became logarithm, right? Compare with square root function. If you have square root, right? If you have squared, we move it to the other side, and suddenly it became square root. This is what we're going to do in this logic 2. So I have 2 to the power of x is equal to 3. Now I take my exponential function, but only base, and I move it to other side, and since it was exponential function before, it became logarithm with the same base as exponential function. So my x will drop because it doesn't have any support anymore, and my 2 moved to the other side and suddenly became as a logarithm with base 2 of 3. And here we obtain exactly the same answer as with logic 1. So it's your choice which logic you would like to use. Now it's your turn to practice.